So, moving into treatment now. Getting back to something that we already talked about, when you think about how injuries happen, there's the injury that happens at that moment, and then there's the cascade of processes that happen after that. And you see this even if you cut your skin. You see that initially it's all kind of clean and it's a mess because there's sort of blood everywhere, but it's clean. But then junk starts to accumulate on it as part of the healing process. And then that junk kind of gets sloughed out and you get left with a scar, right? So in the spinal cord, a very similar process happens. There's a pretty clean injury. There are cells that die. Those slough off. That causes inflammation, and that really extends the process, right? So that's sort of a multi-step model for kind of thinking about how this happens. Now, the way that the signals end up going from the brain down to the legs or the bladder, whatever, is that they go through essentially wires that have to be wrapped with insulation. And part of the promise of what stem cells potentially do is that sometimes some of those wires are still there, but they're just not wrapped with insulation. So maybe there's a way to sort of, one, change how much inflammation happens and stop some of the wiring from being destroyed. And maybe there's also a way to rewrap some of the wires that are there with the insulation that they need to function. And I'll tell you a little bit about probably the study that's the closest to reaching maturity on that. Now, there are scales for figuring out, how impaired somebody is. And they go from A to E. And I'm not going to get into all the details of this, but essentially A means that there's no sensation below the injury and there's no real muscle function below the injury. B means that there's sensation. And C is kind of an interesting break point because you start to get some muscle strength back, but it's not really strong muscle strength back. Okay? Now, when they've looked at some types of clinical trials where they've actually tried to go into the spinal cord and think about injecting something in it, which would be a really good model for putting those brick mason kind of cells in there, what they've seen is that you can potentially make a little bit of a change in this. So if you took patients, if you took patients and you looked at just historically how likely someone is to go from A to B to that C, where I was saying that's kind of the break point where you're starting to get some muscle strength back. Historically what you'd see is that if you started at A, the chance that you would get to C would be less than 10%. So the historical trend has been that it's pretty unlikely to get beyond some muscle strength, really not even to get necessarily back to full muscle strength. When they did some of these interventions, and this particular intervention was really getting to the idea of sort of more like a fireman model, trying to decrease the inflammation. They saw that if you did that, you could get, after a year, where 3 out of the 8 patients they did that with actually ended up making it to C. Right? So you're talking about, if historically you should see less than 10%, this is seeing more than 30% of those patients actually making some recovery. Through a model that would be to do a surgery, you'd actually go in, inject something into the spinal cord, and see whether you could change how that whole scar process that I started to talk about happens. Now, that study, remember I started off with this concept of being funded by independent public funds versus scientific funds. Nobody knows whether this actually would work or not, because it never made it out of clinical trials. The first part seemed to be super promising. We were looking at getting to 30% improvement in terms of 30% recovery to Asia C kind of level, where you have some muscle strength. But when it got into the second phase, the company essentially said, well, we ran out of money, so we just stopped doing it. Right? And that, I think, in some ways is part of the problem if you don't have the public funds to really get to the answer. Right? If there's something that's going on, and maybe there's some promise and maybe there isn't, you just don't get the information. If it's publicly funded, you're obligated to get that information out and say, this either did work or it didn't work. So we're sort of left with this promise of a cure that, or at least improvement, that none of us are ever going to know whether it works or not. That's an important historical thing that happened. That happened in the 90s. And Valley Medical Center was a member in getting patients into this type of clinical trial. But it wasn't stem cells, but it laid a foundation for us to think about how stem cells work. So really the foundation for what we're currently thinking about on stem cell trials that could happen right now, they were driven by an article by a researcher named Hans Kirstead. And what he did is he took embryonic stem cells that were actually from that original set of stem cells. They were actually part of the Bush stem cells. They had lived for 11 years. At this point, they hadn't lived quite that long, but he took those, he differentiated them into being cells that were in the nervous system, and he proved, at least in mice, that you could make a difference in some outcomes from them. And I'm going to show you some movies that give you a little bit of a handle on how that happens. Movies are always kind of tricky in presentation, so let's see if this works. So the point of this first video is just to say in an animal model, you can make a model where you can actually look at very specific things about whether the animal can lift their tail off the ground, whether they can keep their feet close together, whether they can have conjugation between what their front legs are doing and their back legs are doing. And the scientific part of why that works isn't all that important. It's just to say, just like I mentioned that there's sort of an ASIA scale, A, B, C, D, for grading whether you're recovering from a spinal cord injury, there are models for that in animals. And this next video really shows you how the surgery would potentially work. So if you have an animal that has an injury, and you end up going in and looking at what's going on, and you see that area that has a scar, and that scar hasn't fully matured at that point. If you look a little bit closer, what you see is these flashes are essentially signals going through the wires that have the insulation on them. So in order for the signals to go past, there are cells like this blue cell in the middle that have to actually wrap the insulation. And one of the models is that those cells die and the signals can't get past the wires because there's no insulation for that to travel in, the signal to travel in. If you went in with a surgery and injected stem cells that were designated to become part of that wiring system, they could go back and do the brick mason work of rewiring, and then the signals could actually pass through. So you could potentially get recovery in terms of what was going on below the level of the injury. And that's actually the current model for thinking about probably one of the most promising ideas in stem cells now. When they did that in that animal model, what they showed is that if they put them in at about day 7, by the time they got to day 11, there was a pretty significant difference. In fact, it was statistically significant within about a week. So within a week, they showed that you could make a difference that you could actually measure on a scale in terms of the animal being able to walk.